Great. So thanks for joining us, everybody. This is our third seminar for the CUAHSI Cyberseminar Series on data science and machine learning. Today we have Dr. Alex Sun, who's a senior research scientist with University of Texas at Austin's Bureau of Economic Geology. Dr. Sun is a civil engineer by training and is currently involved with both water and energy related research. And today he's going to talk a little bit about some of his research that uses machine learning and deep learning. And if you look at his previous publication record, this is only one of many applications of these types of this type of work that Alex is involved in. So I hope you all enjoy it. Thank you very much for joining us.
All right. Thank you, Gray, for the introduction, and thanks, CUAHSI, for organizing this wonderful Cyberseminar Series on machine learning. So I myself have already learned a lot from the previous two talks. So in this talk today, I will present our recent work on using a deep convolutional neural net for fusing the GRACE satellite data. So these results were originally presented in a WR paper published earlier this year. I'd like to acknowledge my collaborators who are involved in this work, Bridget Scanning and Zhijian Zhang, for helping with problem design, data processing, and interpretation, and David Walling and Zhizhong for helping with some of the algorithm design and implementation, and also our collaborators, Drs. Banja and Mukherjee, for the helping with the in situ data. So this is hard to read a technical magazine or go to a technical conference without hearing about those buzzwords like AI, big data, analytics, machine learning, deep learning, and IoT, Internet of Things, right? So indeed, AI-driven applications have already influenced our daily lives in many different ways. For those of you who are old enough to remember the dot-com bubble in the late 1990s, a recent Fortune magazine article tried to argue that the recent wave of AI is more than just a fad. So first of all, it's built on faster computing power and big data, right? And then secondly, it's driven by a lot of real problems, real interest, and real needs in many different disciplines. And thirdly, and most importantly, is probably that a large group of researchers are behind the current AI-related research. So the hydrological community has been experimenting with various machine learning algorithms for a long time, for several decades, right? So, but if multivariate regression is also considered a special type of machine learning algorithm, then that history could be much longer. So then the important question to ask at this time is what is new and how can we do differently this time, right? So before addressing that question, let me first briefly define the terms. So for the purpose of this seminar today, AI covers all aspects of the computer science that involves the use of computers to imitate human behaviors. And machine learning is a special branch of AI that aims to learn and act like what humans do, right? And then to continuously improve the learned behavior over time in somewhat autonomous fashion. And the deep learning, which is the main interest of this talk today, is a new breed of machine learning algorithms for learning this so-called deep representation of data at multiple levels of abstraction, right? So here, representation is loosely defined as a term like an approximation of the input-output relationship. So each level of abstraction uses the representation produced by the previous level as input and produces a new representation as output. So then this kind of learning is repeated a number of times, as I will show later in my talk today. So artificial neural nets actually has been studied for a long time, as shown on this timeline plot. The first neural net appeared probably in 1940s. Then for a couple of decades, it didn't make much progress until the introduction of this backpropagation algorithm in the mid 1970s, right? So then in 1980s and 1990s, some early versions of the deep learning algorithms we see today started to appear. These include the multi-layer perceptron neural net, the Boltzmann machine, the recursive neural net, restricted Boltzmann machine, and convolution neural net, and of course, the LSTM that were presented in the last two talks. So it's now widely believed that the deep learning era started with the publication of this 2006 paper by Geoffrey Hinton and his group. So in that paper, they sort of showed that how the network with many layers could be trained efficiently. Since then, the deep learning era really flourished with more and more algorithms and tools becoming available. So for his contribution, Hinton recently received the 2018 Turing Award, which is kind of like the Nobel Prize in computing. So many of you may have heard about the fourth paradigm, which is originated from data science. So the main argument is that many scientific disciplines have historically gone through empiricalism, theory, and model simulations, right? And now researchers should embrace data science as a new paradigm by using the tools arising from data analytics for knowledge discovery. So here I use geoscience as an example, but you can readily plug in your own domain of research. To me, the most fascinating part of deep learning is its capability for fusing these image-like observations or data products, which in my opinion may have huge implications for surface and subsurface hydrology, especially because images and multidimensional models are commonly used in both of these domains these days. So going back to my initial question, I believe what is new this time is we can develop more powerful deep learning models that not only have more capacity, but also can extract and learn this multi-scale spatial temporal patterns in high-dimensional data sets. This is a very important capacity. So with this in mind, let me go to the main topic of my talk today, which is concerned with using the deep learning to connect remote sensing and global hydrological modeling. The GRACE satellite, which is short for Gravity Recovery and Climate Experiment, was a joint satellite mission launched by the US NASA and German Space Agency back in 2002. GRACE consisted of two identical satellites that flies about 220 kilometers apart. So these satellites together measure the mass anomalies on Earth. Because most of the mass changes are related to the movement of fluids in the hydrosphere, GRACE satellites provided an unprecedented opportunity for hydrologists to study the global terrestrial water storage change, which is traditionally very difficult or even infeasible because of the lack of in situ data coverage. So the first GRACE mission was ended back in 2017, and the second generation of GRACE, which is better known as GRACE follow-on, was launched in May 2018, but the first data will not be released until early summer this year. So here I highlight this term TWSA, which I will refer to repeatedly in the rest of my talk today. During its mission life, GRACE had enabled a large number of high-impact studies around the globe, which were summarized in this nice plot prepared by, published by Matt Rudell and his group last year. So the color on this plot indicates the magnitude of a long-term trend that fits to the GRACE monthly time series for the period from April 2002 to March 2016. So the cause of the trend in each of this outline study area is explained briefly on the margin of this plot, right? So the blue colors here indicate a long-term gaining trend, while the red colors correspond to areas that have gone through long-term drought or groundwater depletion or glacial loss. So in the US, for example, the hot spots include the Central Valley and Southern California that were caused by droughts and long-term groundwater depletion, and also in the Texas and Southern High Plains that were also related to sporadic droughts. So the actual resolution of GRACE is actually relatively coarse, so which limits its applications to regional and continental scale studies. Nevertheless, there's a strong interest within the hydrological community, especially the global hydrological modelers, to history match the GRACE data using the global hydrological models. So this is because GRACE essentially represents a new source of calibration information, right? So the problem with some of the existing hydrological models is that, they're not originally designed for the purpose other than the, they were not designed for simulating the TWS. They have different degrees of uncertainty when it comes to simulating the total water storage. This may be caused by unmodeled missing processes or uncertain forcing data or uncertain the model parameters. So in the GRACE community, one of the most commonly used global hydrological models is NOAA. It's part of the global land data assimilation system developed by US NASA. So GLDAS includes 4 land surface models, NOAA, CLM, MOSAIC, and VIC. So as shown in this schematic plot on the right-hand side of the slide, the NOAA model has 4 soil layers, and it simulates this exchange of surface water and energy fluxes at the soil-atmosphere interface, right? So it's kind of a relatively complicated model. But Currently, NOAA does not simulate groundwater storage, nor does it include surface water storage and also human intervention. So in a recent model comparison study published by my colleague Bridget Scannon, she found a large discrepancy between GRACE-derived TWS and the model simulated TWS. The models she considered include the all the models in the GLDS family, and also the two global hydrological models, WGHM and PCR Globe. So these plots show the comparison of TWS anomalies for a large number of global river basins. Here the dark line on each of the subplot correspond to the GRACE data, and the color lines correspond to the model outputs. So in general, we see the model results show a large spread, right? And there's a poor correlation between the models and the GRACE, and also among the models themselves. So this mismatch between models and GRACE observations may be a main concern, because these models are increasingly being used for global water security assessment under the current and future conditions. So the main objective of our study is therefore to apply a deep learning method to learn this mismatch pattern between the model simulated TWS and the GRACE observations. So technically, the problem may be considered as a model calibration problem, right? So in which we want to fuse information from GRACE data to compensate for the model deficiencies. So there are at least three different ways for approaching this problem. The traditional way of doing this is through batch calibration or a data assimilation, right? For example, here's an incomplete list of the recent data assimilation studies using GRACE. Some of these approaches perform the so-called model state update to make model outputs consistent with GRACE data, right? So it's found in general that GRACE data assimilation provides significant improvements in soil moisture, and in some models also groundwater estimates. And another approach is that to jointly update both the model state and model parameters. So on the other end of the spectrum, so to speak, we can also develop these so-called data-driven models that can learn this input and output relationship. So these models perform very well. I mean, they can achieve very high accuracy, right? But the main problem is that they do not offer much physical interpretation, right? So the third approach, which is the one we pursue in this study, is what we call the hybrid approach. And so the benefit of this approach is that we can combine we can learn the data, and yet we still preserve some of the complexity in those process-based models. So in also after we submitted the paper, I also noticed there's actually a lot of discussion on this kind of related research. Some people call the approach like theory-guided data science, or some people call it physics-informed data science. So these are all closely related to the method I'm going to describe here. But the main difference here is that we're mainly interested in compensating the existing physics-based model through data fusion. but some of the other approaches are being used to learn this input-output relationship in, for example, in a model governed by a partial differential equation. So for the purpose of this study, we defined the mismatch pattern as a difference between the NOAA simulated TWS and the GRACE TWS. So by definition, the ST, or the mismatch pattern, is a spatial temporal variable. So we formulate this supervised learning problem as shown in this workflow diagram. So for training, the inputs are the model simulated TWS and other predictors if it's necessary. And the target variable is the mismatch between the NOAA TWS and GRACE, or the so-called ST, right? So after this deep learning model is trained and validated, we can use the model to predict this mismatch without requiring the GRACE data anymore. So the predicted mismatch can be subtracted from the NOAA output in order to get the so-called deep learning corrected TWS. So as you can see here, a direct consequence of our approach is that our model can also be used to bridge the data gap when when there's no GRACE data, right? So that can be either before the first GRACE mission or between the two GRACE missions. And also, as you can see from this flow diagram, the deep learning essentially explores the same information as what the traditional data assimilation does. So the main difference is that data assimilation methods often require the modeler to specify some kind of parametric model for the spatial and the temporal error distribution, right? So that's not always obvious. So although the theory behind data assimilation is actually quite general, but most implementations tend to only explore the second order statistics. So here, the deep learning methods implicitly learn the spatial temporal patterns from the training data without requiring many assumptions from the end user. So this is very make our lives much easier. So our model is implemented using a deep convolutional neural net, or DCNN. The convolutional layer is one of the basic building blocks of deep learning models. So I believe most of the audience are already familiar with CNN. So here I simply provide this one slide memory refresher here. So the design of CNN mimics the animal visual cortex by scanning the orientation, shape, and color of objects for patterns. So to do this with a computer, CNN uses kernels to scan the input image both horizontally and vertically, right? So to extract the so-called feature map, during each scan, a dot product is taken between the receptive field and this kernel, right? So we get one value here. By keep on doing this, we get this feature map. A typical deep convolutional neural network model may involve a large number of these convolutional layers, and each layer in turn may also consist of a large number of filters to extract this hierarchy of feature maps or representations of the input data, right? So this the weights of these filters are the unknowns to be solved during network training. In addition, the typical deep learning deep learning model may also use some other constructs like the dropout layer, the pooling layer, and the normalization layer to help mitigate overfitting and to also to improve the training efficiency. On this slide, this diagram shows the general design, the architecture design that we use in this study. So the architecture consists of two major layers. So here we call it stage 1 and stage 2, right? So the main functionality of this top tier is for putting the different predictors together without much feature extraction. So we only provide the so-called very shallow learning here. And internally, all these different predictors are images and are stored as tensors. So because most of these variables also exhibit strong temporal autocorrelation, we also allow the users to stack the spatial images from different antecedent steps together. So the input is essentially a volume. The number of lags is tuning variable that need to be adjusted for different models. So in this second tier, the predictors are merged or combined and then feed to another deep learning model. So our general strategy here is that we use established architecture as much as possible to to do most of the heavy lifting of feature extraction. And we only fine tune these architectures to see if there's further performance improvement. Specifically for this study, we experimented with three different established architectures. So the first architecture we consider is called VGG16. VGG16 is a deep convolutional neural network model originally proposed around 2014 by two researchers from the visual geometry group at the University of Oxford. So that's why it's called VGG, right? So the model is pre-trained on ImageNet, which is a large image database including more than 1 million labeled images and also in a large number of different categories. Because most of the domains we deal with do not have such a large number of labeled training data, so VGG16 or similar pre-trained models are often used to demonstrate this notion of transfer learning. So in which a model is first trained on an information-rich domain, such as using this large image data set, and then applied to the sort of information per domain. So one more example is this Stanford poverty mapping project, in which a VGG model was used to infer the poverty map in African countries using these satellite netlines as a proxy, right? So VGG16 was originally introduced in 2014, which is actually already quite old in the deep learning standard. For example, the design involves this fully connected layers, which means each neuron is connected to all neurons in its previous layer. So this actually increases the number of unknowns significantly. And the second architecture we consider in this study is UNet, which was introduced around 2015. It got its name because this U-shape architecture The first pass is so-called the downsampling pass or the contraction pass, and which is then followed by this expansion pass or the upsampling pass. So also UNet uses this so-called scape connections to combine the local features or fine-grained features from the downsampling step with this coarse-grained information from this upsampling step. So so the purpose is to restore the lost information from this contraction step, because contraction sort of is a downsampling and it focuses on the fine-grained information. So for this reason, UNet also belongs to this class of encoder-decoder networks, where the inputs are sort of projected to a smaller feature space and then mapped to output in a potentially different domain. So UNet has demonstrated a lot of success in image segmentation problems. And the last architecture we consider in this study is an architecture that is similar to UNet, both involving this encoding and decoding steps. The main difference is that in the design of decoding steps, the so-called segment-like use transposed convolutional layers instead of the upsampling layers. So as a result, the number of unknown parameters is significantly reduced. Also note that both UNet and SegNet do not involve the fully connected layers. So for the our case study, we will focus on the country of India. And this region is very important. Nearly 1/5 of the Earth's total freshwater storage can be found in this Himalaya region, and which is home actually to more than 1.7 billion people. A large of annual rainfall budget over the India subcontinent may be attributed to the India summer monsoon, which is modulated by this steep topography of the Himalayas. The entire India region, except for the southern part, receives this maximum precipitation during the monsoon season, which typically lasts from June to September of most of the years. So during the dry season, the surface water is typically scarce, and the groundwater becomes an important alternative. So this Indus, Ganges, Brahmaputra system form a regional alluvial aquifer system, and that is one of the most productive aquifers of the world. Irrigation withdrawal currently accounts for about 90% of the total groundwater uses in those areas. So the map on the right of the slide here shows the percentage of irrigated areas, which is mostly concentrated in northern India, in Pakistan, and central and northern Bangladesh. So overuse of groundwater in the past several decades has caused pronounced groundwater depletion in northwest India. In fact, groundwater depletion in northwest India was actually among the first TWS trends revealed by GRACE. So the Indian government has set up an extensive in situ groundwater monitoring network. So this map here shows that more than 50% of the monitoring wells are showing some signs of a water level decline. So again, this slide was from Bridget et al.'s study. It shows this model GRACE comparison for two largest river basins in India, the Indus and the Ganges. The top plot are the decision TWS anomalies, and the bottom plot is the cumulative precipitation anomalies. So over these basins, GRACE detected a long-term declining trend, while NOAA, which is shown as this light green line, does not show any discernible trend, long-term trend. So here it shows the setup of a deep learning model. The size of the domain is 40 by 40 degree, and it's discretized into 128 by 128 grid through bilinear interpolation. So climate in this Himalaya region is very complex, as I just mentioned. So then that's why we set this model, the area, to be much larger than the actual study area. Intuitively, that would help the deep learning model to pick up the large-scale spatial patterns that go beyond India, right? So we first did an exploratory study to understand the spatial and temporal TWS patterns. So this plot shows the monthly averaged GRACE TWS. So as can be seen from this plot, most of the areas show positive TWS anomalies during and after the monsoon season, right? Starting July, August, and all the way to November. And then on the other hand, the TWS anomalies are mostly negative in the dry season, especially from March to May. So this next slide shows the same shows the monthly average mismatch pattern. Recall this mismatch is the difference between NOAA and GRACE. So because of the missing processes in NOAA, it tends to underestimate the magnitude of TWS. So the positive values on these plots indicate that NOAA TWS is less negative than the GRACE TWS. And so it mostly happened during the dry seasons. And in the wet season, it's the opposite. The NOAA TWS is less positive than the GRACE TWS. So by visual inspection, we see that the mismatch patterns show a good temporal correlation with GRACE TWS patterns, only the sign is opposite. So to train our deep learning model, we define this weighted loss function, which is weighted sum of mean square error and modified form of Nash efficiency. The solver we use is stochastic gradient descent with this adaptive learning rate. So the learning rate is basically a hyperparameter. So if the learning rate is set too low, training will progress very slowly. However, if the learning rate is set too high, it can cause undesirable divergent behavior in the loss function. So it is therefore desirable to reduce the learning rate when the optimal solution is approached. And the table shows the training time for each epoch. The VGG16 is the biggest model, and therefore is the slowest to train, and taking about 4 seconds on the NVIDIA K80 GPU. So the segment light is the smallest model, and it took less than 1 second to train on the same GPU. So we use 125 miles for training and the rest for validation and testing. Because GRACE is coarse resolution, right? So the GRACE community is mostly interested in the basin or country average results. So for that purpose, we also calculate the Nash efficiency on the basin average, the TWSA. So here it shows results at the country average level. We see that deep learning improved the model fit significantly, as shown in this top plot here. And all three models were able to improve over the original NOAA, which is used as baseline and shown as this dotted line here. And among the three, the Segner Light model achieved the best performance. And so it's also supported by the bottom two plots here, which show the cumulative distribution of the correlation and the Nash efficiency at the grid scale. So this show the actual results we obtained from the grid scale. The top row corresponds to a correlation coefficient at each grid cell, and the bottom row shows Nash efficiency. And so the first column corresponds to NOAA TWS. The second line corresponds to the Segner Light results, and the third column shows the improvement due to deep learning correction. So as we can see here, that deep learning was able to make better, improve the model over most of the study areas, especially in the northwest India. On the other hand, we also observed some kind of performance degradation in some of the in the Ganges Basin, and also in the isolated spot in the southeastern coastal area, and also somewhere in this the Brahmaputra, the upstream of Brahmaputra River Basin. So comparing to the long-term precipitation map and also the irrigated area map we showed before, we see that these performance degradation regions correspond to either sharp changes in the precipitation gradient patterns, or to areas of strong human intervention, in this spot and also in the northern India. So as some kind of point check, we zoom into the two grid cells with good fit. So here, point A is located in northwest India, and point B is in the south central India. So in both of these 2 points, deep learning was showing to improve the model fits significantly. We also looked into two grid cells with not so good fit. So one in the India-Nepal border, and the other is in that isolated spot near the southeastern coast. So as a carry-away message, the possible explanation for the cause of this performance degradation might be, although we use a relatively large buffer area, it may not be large enough to extract all the large-scale patterns. And the other main problem, or probably a more fundamental problem, is that we're getting very small training data set, right? So we only have like around 125 months. So these days, there may be better tools such as semi-supervised learning that can be used to deal with this small training sample problem. And that's something we're going to look or investigate in our future work. And as I mentioned before, for one of the main reasons we chose India for this case study is the availability of a large amount of in situ groundwater data, which were converted to groundwater storage data by our collaborators. So here we compare the learned mismatch pattern with the in situ data. So this plot shows the correlation between the mismatch pattern and the in situ derived groundwater storage is mostly positive, and for most of the wells. This is really encouraging. It provides evidence that deep learning mostly corrected the missing groundwater storage component in the NOAA model. So our original study period ended in December 2016. And as an additional test, we applied this trained model to the remaining GRACE data that were not used in the original training and validation tests. We also gave a prediction after the GRACE mission ended in the summer of 2016. So for all these predictions, we only use NOAA simulated TWS as the input variable. So the results show that our model gave a relatively satisfactory performance during this additional testing period. So here the shaded area is the prediction interval that's calculated using the model misfit residual from the training period. So in summary, in this study, we developed a deep learning-based method for reconstructing TWS using a land surface model and GRACE observations. So compared to the existing methods, deep learning requires fewer assumptions and can easily handle different predictors. For our particular case study at hand, we found NOAA TWS alone was actually sufficient to capture the main system dynamics. We experimented with additional predictors such as precipitation and temperature, and we did not notice significant improvement. For other basins, though, there may be a weaker correlation between NOAA and GRACE, and additional predictors may be necessary. So the main message from this talk is that deep learning is very promising, but it is not a silver bullet. It still requires a lot of domain insight and to frame the problem right and to get the results right. And to conclude my talk, I'd like to quote this following comment from the CEO of an AI company. AI is a journey. It's not something you can buy and suddenly flip a switch. So by the very definition of AI, it takes time to learn. So the implication is that for the hydrological community, the only way to learn is to work on more real problems, right? So this is a number of deep learning related articles we found in scopes that are related to hydrology and also to remote sensing. The field of hydrology had a relatively late start compared to some other fields. But there's tremendous interest as indicated by this trend in published articles in the last several years. So with this, I conclude my talk, and thank you very much for attending. And here's a list of references I mentioned in my talk today. Okay, thanks.
Great. So thanks, Alex, for sharing that. We have 3 questions, and I'm going to start with the first one here because it was actually the same question that I had while while listening to what you're saying. So the total water storage has a strong memory. It's a state variable in a dynamic system with some sort of time series component. Have you tried integrating a time series component into your deep learning model like an LSTM?
Yeah, that's a good question. Actually, we began by testing using a convolutional COV LSTM, right? So well, at least in our case, we found the COV LSTM was did not give as the performance was not as good as the model architectures we use. So here basically we use this channel dimension of the tensor to store the TWS from antecedent steps. So that's used to account for this the memory effect you just mentioned.
Great. So on a related note, one of the other questioners asked why a convolutional neural network did the ANN perform poorly. And let me just add to that. Did you find value by looking spatially rather than looking at each grid point individually?
That's a great question. So the short answer is no, but the long answer is that GRACE is actually the actual resolution is not at the degree level. So we that's why we tended to focus more on this the so-called regional average behavior. So if we I guess for other problems, technically, we could do it at the grid level. And so as you saw from my the loss function, so we actually enforce this kind of, the regional match, right? So there are many different ways to tweak that loss function in order to improve also the local match, at fine grain at the finer level, right? So maybe that's something to play with in the future, but right now, we didn't focus on at the grid level.
On slides 30 and 32, there looks to be a time shift between the NOAA total water storage and GRACE. I think you just explained how you got that, but can you cover that again? How did your model pick up on this time shift?
Well, I mean, that's probably the magic power of deep learning, right?
So is it shifting at every time step individually, or is it looking at the time series as a whole?
It's probably pick up from this mismatch pattern from the training period, because this lag may be consistent, right? Mm-hmm. So it's consistent for in all the training samples, then that's how the deep learning pick up this mismatch in correlation.
So it's picking up that periodic shift purely from a time slice perspective. And the fact that it is a periodic shift, right? So if there was a trend, do you see any potential for that? Since it's learning basically a periodic shift by only seeing one time slice at a time, do you have any worry that if there's some major non-stationarities that it might not pick up on that?
Major non-stationarity, you mean like a declining trend, right?
Or a change in the amplitude of the periodic signal in either NOAA or GRACE, or some other type of thing that sort of shifts that, changes that periodic shift a little bit.
Yeah, that's a good question. So I suspect that will cause problem, because this deep learning is basically the basic principles are the same as the traditional machine learning, right? So you have to train the model and give it all the possible the scenarios or training samples in order for it to recognize this shift in the train. Otherwise, if your model is trained on the samples that do not have such trained, and then suddenly this trained, there's an abrupt change in the train. I think that may cause problem in the deep learning model. But of course, you may try other methods, like give your deep learning model some hint, like certain additional predictor. That may help the deep learning method to recognize this the abrupt change or the breaking point.
So one person asked about whether you know any other features or human intervention factors related to human intervention that you might include as features into your model.
Well, that's also a great question, and we didn't in this study, but for human intervention, irrigated area, I believe there's some data sets available. Then the question is, how do you incorporate that into a deep learning model? So that's kind of like almost like I guess some of the discussions we talked about during the last presentation, right? How to add this static information, right? Or the human intervention may actually not be static, but it's just this, how to give the deep learning model this additional information. So technically, the user may try to add this, additional image, just as some kind of additional hint or condition during training. But we haven't tried it ourselves, so we don't know whether it's going to work or not.
So I guess you made a comparison with data simulation earlier. I guess one of the advantages here is that you can introduce new hypothetical inputs into your deep learning model in a way that's somewhat simpler than if you were trying to do that in the data simulation context. Do you agree with that?
Yeah, I totally agree. I think you also alluded to some of that in your talk, 2 weeks ago. So the deep learning and data simulation share many similarities, but many of the traditional data simulation require kind of some kind of a parametric covariance model. So that, in my opinion, is not very easy. And also, many of the methods probably would require modification of the process-based model. So that may not always be possible, right?
So two people have asked about total water storage in NOAA. One person says that slide 10, you mentioned that hydrological models were not developed to simulate total water storage. So, and asks how you got total water storage out of NOAA. And then one other person proposes that the periodic shift is due to the fact that NOAA doesn't have groundwater and GRACE has groundwater, which has a longer memory. Can you tell us a little bit about the total water storage state in NOAA?
Yeah, sure. So the total water storage in NOAA is actually the summation of soil moisture, and so in India, then also the minor part is probably the snow water equivalent. So those are the two biggest components that are simulated by NOAA. So that's what we call the TWS, knowing that the surface water and the groundwater components actually are not there, right? So that's what we define as the NOAA TWS. But we know that some of the components are actually missing. And so the second question, I'm sorry, what's your second question again?
The second one is someone proposes that this difference, the lack of groundwater in the TWS NOAA estimate could cause that time shift we saw in the previous graph, because groundwater has a longer memory.
Yeah, I agree with that. So that's kind of related to your first question. The cause of this shift between NOAA and NOAA simulated TWS and GRACE, because the groundwater has longer memory effect.
Is there any way in your model to, given the fact that there's sort of a missing state in NOAA that's at least accounting for some of the difference between NOAA and GRACE, is there any way in your model, for your deep learning, to identify a new state variable?
New state variable.
Yes. So I'm just pretending like I didn't know that groundwater was missing in NOAA. Could deep learning tell me, is there some signature of your results that could tell me that NOAA is missing a state variable?
That's possible. So basically, the whole hypothesis is that deep learning could be used to correct for this model structure error, right? So first, I think that's kind of largely almost like a catch-22 problem. Without comparing to observations, we probably do not know how well our model performs, right? So, but after comparing to the observations, we know that certain process is not simulated correctly. And in case of NOAA model, actually we know from the implementation of the model that this process is missing. But like your question is like, will the computer be smart enough to tell what is missing in this model? I mean, maybe in the future, but right now, I'm not there yet.
Cool. So that's all the questions we have. There's still 36 people. Thank you so much for joining us, and I hope that everyone comes back next week. Thanks very much, Alex.
Yeah, thank you.
And thank you, Alex. I do want to add, if you should look at your screen right now, I listed the upcoming remaining speakers for the series. Xiaopeng is coming back, and he'll be giving his own talk. Same time, around 1 o'clock Eastern. And I also want to point out that we are CUAHSI is accepting abstracts for oral and poster presentations for our conference on hydroinformatics taking place in July in Provo, Utah. We welcome you to submit your abstracts, and we do offer travel grants for student presenters. And then Xiaopeng will also be a keynote speaker there as well. Registration is open. Early bird deadline is June 15th, so please take advantage of those deadlines and travel grants. All right, well, everyone have a great day.